hello my YouTube viewers, how are you? So this is a course of computer organization and architecture. This course will discuss the basic concept of computer architecture and organization that can help the participants to have a clear view as to how a computer system works. Examples and illustration will be mostly based on a popular reduced instruction set computer or RISC platform. Illustrative examples and illustrations will be provided to convey the concept and challenges to the participants. Starting from the basics, participants will be introduced to the state of the art in this field. So, this course topic is evolution of computer system, instruction set architecture, quantitative principles of computer design, control unit design, memory system design, design of cache memory systems, design of arithmetic unit, design of input-output system design and instruction pipeline, parallel processing architectures. Okay. To start with this course, I will come first to evolution of computer system. So we all know that computer has become a part and parcel of our daily lives. We cannot disagree to this fact. We see everywhere computers that is some kind of processing unit. Like when you think about a laptop which we use in our daily use, tablets, mobile phones, which are used by one and all today, and intelligent appliances like of course your smartphone is one part. From that you have a smartwatch and various other applications. So computer has become a part and parcel of our life. So we need to understand how a computer actually works. So what is there inside a computer? So in this particular course we will be seeing all these various aspects where the two terms computer architecture and computer organization will be taken care. Okay. Now coming to what is computer architecture and what is computer organization. The title of the course. So here computer architecture consists of those attributes of the system that are visible to the programmer. By these, what we mean is how the various components of a computer system are integrated to achieve the desired level of performance. In an analogy, I can say that you think of an architect who plans the entire design of your house, but it is ultimately the civil engineers who actually does the exact building, like what kind of construction will be taken care of, right? How the construction will be taken care of, how much percentage of cement bricks will be there, will be taken care by a civil engineer, right? So in that respect, the design of components and functional blocks using which computer systems are built comes to the organizational part. Okay. So I will take a very small example, like you have in your computer some functional blocks like your processor unit. Inside processor unit we will be seeing that we have many other components like register, ALU and other units. I will just take a small example. Let's say I will have an adder, but what kind of adder I will be having, that is to the discretion of the computer organization, whether we will be have a carry save adder or a carry look ahead adder or anything else. So these are the two different aspects of computer organization and computer architecture that we will be seeing in this particular course. Okay. Coming to the historical perspective, how computer have evolved over the years. So whenever there is a need for doing certain things, then only something comes up, like a constant quest of building automatic computing machines have driven the development of computers. So in the initial efforts some mechanical devices like pulleys, levers, gears were built. During World War II, mechanical relays were used to perform some kind of computation, like using a small relays, people design circuits to carry out the operations. Okay, so then comes the vacuum tubes, using which the first electronic computer called ENIAC was developed. And from then semiconductor transistor were developed. When semiconductor transistor came into the picture, then the journey of miniaturization started. First with small scale integration, then people moved with the medium scale integration, and then large scale integration, then to very large scale integration, and how the era of ultra large scale integration where we stand today. Okay, so this is the first mechanical calculator we have seen that was invented by B. Pascal. So this particular calculator could add only two numbers. It can only add two numbers, or it can only subtract two numbers. And if you wanted to do multiplication or division, it could have been done by repeated addition or repeated subtraction. Okay. So then the Babbage engine came. This was the first automatic computing engine designed by the father of computer, Charles Babbage, in the 9th century. But he could not build that, only he designed that. Later in 2002, that is 153 years after its design, it was built, and it consists of 8,000 parts, and it weighted 5 tons, and it was 11 feet in length. So you can imagine how large it is. Okay. So the first electronic computer was built, which is called ENIAC, Electrical Numerical Integrator and Calculator. It was developed by University of Pennsylvania, and it uses 18,000 vacuum tubes and weighted 30 ton, and it also occupied a very large space, which is 30 feet cross 50 feet. So what is vacuum tube? Vacuum tube is a device that controls electronic current between electrodes in an evacuated container in a tube. So using those vacuum tubes, the first computer ENIAC was built. It also dissipated a huge amount of heat. Next was Harvard Mark I. This was built at the University of Harvard in 1944 with support from IBM, and it uses mechanical relays, and of course some electric signals were also used to work with the relays to represent the data. And it also weighted 35 tons, and it requires 500 miles of wiring. So these are the computers which were built in the carry in early stages. Then come in 60s and 70s, where the popular mainframe computer came into the picture. So this popular computer IBM System 316 was introduced. It introduced many advanced architectural concepts that we use today. But you can see from the picture that how big it was. But as I said, some of my architectural aspects of concept that were used in that computer appeared in the today's microprocessor several decades later. Okay. Now we stand where the modern processor chips comes in dual core, quad core, and also in 6-core variants. So you can see that how many core today's computer has, where each core is a 64-bit processor that comes with the various microarchitectures. These are the various microarchitecture within and 70, where they are called Haskell, Nehalem, Sandy Bridge, etc. Now coming to the generation of computers. So broadly we can classify the growth of computer, how computer has evolved into some generations. So this actually represents some features of operating systems and representative machines. So between the years 1945 to 54, vacuum tubes and relays were used, and the representative system used machine language. So if you want to enter some data into the computer for processing, you have to enter in machine language, right? Or either in assembly language. No high level language were used to enter the data. Then comes the second generation, where the transistor, memories, IO processors are the main technologies. Here batch processing is the performed, and you could enter the data in high level language. Then comes the third generation, where we were into semiconductor industry, where the small integration and medium scale integrated circuit were used. And in the IBM 360, Intel 8008, where the first one to make the step into this computer market. Then in the fourth and fifth generation, this large scale integration and very large scale integration came into picture, and we could see multiprocessors. Now what has happened is like the space has become larger because the components that we use to build those basic blocks has become smaller. So in the same space where earlier we could keep a small number of components, now we could keep more number of components, right, into the same space, and hence multiprocessors comes into pictures. And now we are in the era of ultra large scale integration with many scalable architecture and post CMOS technologies. Now we also have massively parallel processors like Pentium, Sun Ultra, Workstation, etc. Now you see that evolution of these types of computer. So initially mainframes came in the year of 60s and late 70s, in between 60s and 70s. Then came mini computers, then came workstation, and finally we see personal computers, like, and then further we see laptops and smartphones. So every smartphone today is having some processing capability. That is why we call it a smartphone with some smart features into it. And we also have now millimeter scale sensors, and these are not only sensors that is will sense something, rather these sensors are having some intelligent capability, like some processing capability which can process those data that are collected from the sensors. And also it has a communication feature, so that it can communicate to others if required. So these millimeter scale sensors have both the capabilities of processing as well as computation. So we can see how the evolution of types of computer system have come up, and now where we stand in the future. We will see large scale IoT based system where these sensors itself are very small, where they will have not only the sense capability but also processing capability, right? Now you see the evolution of PC form factors over the years. This is the first standard ATX, where you can see the motherboard slot, you can see this is a motherboard, you can see the processor, you can see the slots of memories for all the components. Now how the miniaturizations has taken place. First it was standard ATX, then micro ATX, then goes mini ITX, now nano ITX, now we are in pico ITX, right? So we are in the era of miniaturizations, and now the miniaturizations, of course, we are able to do some good thing of performance, but at the same time power issue is one of the important factors that we have also handled, which we cannot deny. Now this is the famous Moore's law that refers to an observation made by Intel co-founder Gordon Moore in 1965, which he noticed is that the number of transistors per square inch of integrated circuits had doubled every year since inventions, and this law predicts that this trend will continue into the foreseeable picture. But now Moore's law stands here, where it says that number of transistors that can be placed in an integrated circuit gets doubled in every 18 months, and this has held over a period. Like you can say that now you can see this diagram, which is how the Moore's law works. This is the number of transistors per chip, and this is over the years how it has grown. So this straight line actually indicates that Moore's law holds, and starting from 40004 we are now in IVY bridge, Sandy bridge, and various architectural advancement has taken place. A number of transistors that can be put in a chip has doubled in every 18 months, and as long as it is a straight line, we can say that Moore's law holds. So at the end, if you learn something from my video content, so at least like, share and subscribe my channel, and in the next upcoming video I will help you some computer science related videos. Okay, so goodbye, have a nice day.